In section 9.4, we're going to take a look at the properties of logarithms. We have defined in the earlier section 9.3, what a logarithm is in terms of being the inverse of the exponential, right? The logarithm of a number is we're trying to find what number do I raise the base to get to the inside of the logarithm. Now, what we want to look at now is some interesting properties that the logarithm function has that makes it different from a lot of the other types of functions that we work with. And some of those properties are going to, actually there's three of them. We're going to look at the product rule, the quotient rule, and the power rule, and use them to simplify logarithmic expressions. A key step in solving equations, which is what we'll be ready to look at after we've finished this section. The first property is called the product rule. And in the product rule, we have that the following statement is true, that if you had the log base A of two numbers multiplied together, assuming those are real numbers, and of course the base is anything that's positive and not zero, we can do the following. The log of a product, remember that two things multiplied together is called a product, is equal to the log base A of the first factor plus log base A of the second factor. Now, why is that true? Why does the product inside the logarithm turn into a sum between the two logarithms? Well, it's because logarithms are, in essence, just exponents. Remember, if I have log base A of x equals y, I'm saying a to the y power is equal to x, right? The output of the logarithm, the number you get out of it, is the exponent. And there's a rule that says when you multiply two exponential expressions together, what happens to their insides, or what happens to the exponents, they get added together. So what that means is that log base 3 of 5 times 7 is log base 3 plus, log base 3, and let's do this in red so you know we're doing an example here, like problems you will see in your homework. That says this is log base 3 of 5 plus log base 3 of 7. That is, if I were to take and multiply this together, get 35, and then take the log base 3 of 35, say in my calculator, I would get the same answer as if I were to separately take log base 3 of 5 and log base 3 of 7 and add those two numbers together. We can also do it when we had variables involved. So this log base 4 of 3x would be log base 4 of 3. Because there's an understood multiplication in between here, I would add log base 4 of x. A product inside becomes a sum between two of the same kind of logarithm. That's the product rule. The second rule is called the quotient rule, which if a product becomes a sum, right, there's a connection between multiplication and addition, then it's natural to assume that a division problem, or a quotient, is going to become a subtraction problem. Okay? And it's the same reasoning, right? A to the m over a to the n looks like what? A to the m minus n. So if you have a log of some base of x divided by y, you can rewrite that as log base a of x minus log base a of y. So in this example, log base 8 of 23 over x would be log base 8 of the numerator. Always start with the top and subtract the bottom. Log base 8 of x. We have expanded this expression into two logarithms. We can do the similar thing with the natural log, right? We've seen this as the log base e. So the natural log obeys these properties as well. So this would be natural log of e to the 5th minus the natural log of 11. Now I could stop there, but in fact there's more simplifying that can be done. Look at this. Remember what happens when you take the natural log of e to some power. Right? That's the property that when you have log base b of b to the x, log base b and b to a power cancel out and you're left with the exponent. In this case, natural log has a base of e, so this is like log base e of e, which means that's 5. The log base e and the e cancel, leaving me with just 5 minus the natural log of 11. And unless it's a word problem or the instructions tell you to, don't plug that into your calculator. The last property that we're going to consider in this section is called the power rule. Right? The power rule comes from the fact, well, let me give you a quick little example up here in the upper part of the screen. If I had log base, who cares, 2 of x times x, right? According to the power rule, I'd get log base 2 of x plus log base 2 of x, which is 2 of those, right? It's 2 log base 2 of x. Now what I want you to see here is x times x, of course, is the same thing as log base 2 of x squared. Now what I want you to see here is that this 2 is the same as this 2. Meaning that that 2 up there in the exponent just got pulled down out in front. Okay, and imagine if I had 3 of these, I would end up with 3 here, and I'd have 3 log base 2 of x. So the exponent has the ability to come out front. So whenever you have log base a of a power, that is x to some power, and n is any real number, it doesn't matter if it's a whole number like this or even if it's a fraction or negative number, you can always take that number out front and end up with n log base a of x. Okay, so in the examples below, this 9 could come out front, and I could end up with 9 log base 8, or sorry, log of 8, meaning log base 10. That's common log. Now what about this one? This is a little bit trickier. I've got the cube root. In order to do this, you just have to remember that radicals are also exponents. We learned that back in chapter 7. That's the same as x to the 1/3. Just convert the radicals to fraction exponents. Radicals. Okay? Now you can pull that 1/3 out front and you get 1/3 natural log 1/3 natural log of x. That's your final answer there. This is your final answer up here. Okay, so those are the 3 rules. We got the product rule, we've got the quotient rule, and we've got the power rule. Now how do we use those in combination? That's the next question. Look at this example and notice that we've got several things going on. We've got actually powers, like the 4th and also the 1/3, which is the same thing as the cube root, and we've also got a multiplication. Okay? Now, in order to apply the rules, we have to be able to apply the rules directly as they appeared above, and in this case, I can't pull the 4 out front because I don't have that the entire inside of the logarithm, right? The entire argument here has to be raised to the 4th power in order to pull it out front, which I don't have, right? This one has a 4th power, this one has a 3rd power. So I can't apply the power rule yet, but I can apply the product rule because I have 2 functions, 2 expressions multiplied together. So the product rule says that this would be the same log base b, of the first object, x to the 4th, plus log base b of the cube root of y. Now I can apply the power rule to this logarithm because the entire inside is raised to the 4th. I have log base 4 of x. Sorry, log base b of x. I'm getting ahead of myself, sorry. Of x. And that one's simplified completely because I can't separate it out any further, pull out any other powers. This one, as before, we recognize that that's y to the 1/3, so I'm going to pull the 1/3 out front and have 1/3 log base b of y. And this is as simplified as it can get because, again, I cannot apply any of the 3 rules now. There are no products inside, quotients inside, or powers inside. So I am done. Example B similarly has several of these functions involved. We've got division, we've got multiplication in the denominator, and we've got a radical in the numerator. Now, the only way that I can separate this into 2 functions to begin with is a numerator, or I guess the easiest way to separate this would be the numerator and the denominator, so I would apply the quotient rule. I can't pull out powers yet because the whole inside's not raised to a common power. So I end up with log base 5 of the numerator minus because it's a quotient rule, log base 5 of 25y cubed. Remember that the quotient rule ends up with two logs. Log base 5 of square root of x minus log base 5 of 25y cubed. Now on this first log, I can actually pull the 1/2 out now and be done with it. But this one, I need to separate again because there's a product inside here. So this is going to be subtract. Now be careful here. If you split this into two logs, remember that you have to subtract the entire result. Meaning that if there's a plus inside here, I've got to subtract both terms. So this is going to be log base 5 of 25 plus log base 5 of y cubed. Again, the parentheses because you have to subtract all of what this is, even if it splits up into two separate logarithms. Okay, now let's do this all together. We got 1/2 log base 5 of x minus, if I apply the minus here. By the way, what is log base 5 of 25? 5 to what power gives me 25? The answer is 2. I also need to distribute the minus sign here, so I end up with a minus. But I can also pull the 3 out front, so I end up with 3 log base 5 of y. All my rules have been applied. I cannot apply any more, so that is my final answer. Okay? So all of this is a type of simplifying where we end up with simpler logarithms. We've taken a logarithm of a mess and made simpler logarithms. Another way to simplify, and it makes sense in different contexts, is to take several logs and combine them into one, right? This is a smaller expression than this, right? So in a sense, this could be considered simpler because there's only one log. However, this could also be considered simplified because each log is as simple as it can get, right? So it depends on what you want. And in many cases, we may want to be able to combine these things back into it. So we've gone this direction. What about going back the other way? Can we do that? And of course we can. We can apply the product rule, the quotient rule, and the power rule in reverse. Look at this one. Log base 4 of 2 and log base 4 of 32. I can't find those logs separately. But if I combine these logarithms using the fact that plus becomes a product inside the logarithm, I can change that to log base 4 of 2 times 32. What is 2 times 32? Well, it is 64. And 64 is, in fact, a power of 4, so I can do this one in my head. 4 to the third gives me 64. And so log base 4 of 2 plus log base 4 of 32 is actually just the number 3. Let's do another example where we're doing this to combine logarithms. All right. And in fact, those words, you need to be able to recognize the difference between what we're being asked. In this case, we are asked to combine. Previously, we were expanding. Okay? Expanding the logarithms, and now we're combining logarithms. So let's combine these logarithms into a single logarithm. Now I cannot combine two logs when they have different coefficients. So first thing I'm going to use is the power rule to bring those numbers up inside as exponents. So this becomes log of x to the 1/2 power plus log of x minus 1 to the 4th power. If we add them together, that is now the product inside a single log. So log of x to the 1/2 times x minus 1 to the 4th, which is correct, or alternatively we could also convert x to the 1/2 to a radical, and either one of these last two lines would be correct. We have a single logarithm. Let's do one more, again being asked to combine. We start by making sure that we have 1 in front of each one of these, so I need to bring in the 3 using the power rule. This gives me the natural log of x plus y cubed minus the natural log of x. Now apply the quotient rule because we have the difference of two logs. That's the natural log of the first, which is x plus y over cubed, divided by the natural log of the second, which is x. The last important property that we're going to cover of logarithms is the change of base formula. And this is like saving the best for last. Maybe that's not entirely accurate, but what this allows you to do is to take your calculator and answer any logarithm problem using it. Here is what the formula for the change of base tells us. It tells us that the log base a of any number is equal to any other log we want, say base b, of the number x divided by log base b of the number a. Now what does that mean? That means we can take any one log we want. That is, we're trying to find log base a of x, and a and x are numbers in the problem. If we want to actually calculate it, we can use another log to get that answer. We don't have to use log base a to get the answer. We pick another log, take the log of the inside divided by the log of the base, and we've got it. So this could be log of x over log of a. Now why is that good? That's the common log. Your calculator has a common log. Or natural log. You can do the natural log of x over the natural log of a, and you will get the same answer. Let's test that. Let's look at log base 5 of 40. So we're asking 5 to what power gives me 40? So take log of 40, I'm using common logs because that's what the problem says to do, divided by log of 5. If I do that in my calculator, I take 40, take the log of it, take 5 log of it, and divide the 2, I get 2.292, which makes sense because 5 squared is 25, 5 cubed would be 125, 40 is somewhere between 25 and 125. So this makes sense. Now what if I use natural logs? What if I did natural log of 40 divided by natural log of 5? Dun, 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 dun. 2.292. I get the same answer on my calculator, and that is how we can use our calculators to evaluate any logarithm that we want. Alright, that's the end of section 9.4.